Beneath the cold expanse of space, the James Webb Space Telescope drifts silently, its golden mirrors catching the faint infrared glow of distant stars. For decades, humanity has gazed upward, scanning the heavens with ever more sensitive instruments, hoping, praying, that somewhere beyond our tiny blue planet, we were not alone. But no telescope had ever come close to this level of clarity, this piercing vision into the hidden atmospheres of worlds orbiting stars light years away. Until now. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. On a quiet night, deep within the Mission Control Center, a hush fell over the team. Data streamed in from Webb's instruments, numbers and graphs scrolling across the monitors. There it was, a planet, orbiting a star much like our sun, but thousands of times farther than the most distant satellites in our solar system. And yet, through the veil of distance and dust, it revealed a secret, a whisper from across the galaxy, faint but unmistakable. The atmospheric composition was unlike anything seen before, a tapestry of chemical markers dancing in patterns that could only mean one thing. The team leaned closer, barely breathing, as the preliminary analysis came through. Water vapor, oxygen, methane, carbon dioxide, a precise balance of gases that could not exist in isolation. A signal so clear that it sent chills down the spine of every scientist in the room. And then came the calculation, the figure that would change the course of exoplanetary science forever. A 99.7% probability that this world harbored life. Pause for a moment and imagine that, 99.7%. In human terms, that's nearly certainty. It's the difference between betting on the sun rising tomorrow and knowing, without a shred of doubt, that you will see its golden light. And yet, this certainty comes not from direct observation. No one has set foot on this planet. No probe has landed on its alien soil. Instead, it comes from the meticulous decoding of starlight, the subtle fingerprints left in the spectrum of a world so distant that light itself has taken decades to reach us. Picture the planet, if you can. A world bathed in the glow of its star, oceans glinting like liquid sapphire, skies tinged with clouds that dance and swirl, and the invisible movements of life stirring beneath the surface. Perhaps single-celled organisms drift lazily in the currents of alien seas, or forests of unimaginable shapes sway in the wind. Perhaps the air carries chemical signals from creatures that have no names, no forms familiar to us, yet whose presence we can measure from across the cosmos. Every molecule, every spectral line, is a story waiting to be read, a message etched into the very breath of the planet. It is easy to underestimate what this discovery means. For centuries, humanity looked outward and wondered, are we alone? Philosophers speculated, poets dreamed, scientists calculated probabilities that ranged from infinitesimal to hopeful. Exoplanets were mere dots, distant orbs whose existence we could only infer. Now, Webb has pulled back the curtain. We are not imagining anymore. We are seeing, not with our eyes, but with instruments that translate the universe's hidden language into something comprehensible, something breathtaking. But the thrill of discovery is always tinged with the unknown. We must be careful, deliberate. A 99.7% chance is not absolute proof. Nature is clever, sometimes deceptive. There are processes that can mimic biological signatures, volcanic activity, chemical reactions in the atmosphere, cosmic radiation stirring molecules into patterns that look alive. Yet, the convergence of evidence on this planet is unlike any false positive ever seen. It is a symphony of signals, harmonizing in a way that almost demands one conclusion. This planet teems with life in ways we are only beginning to understand. Now, consider the scale. Light years are not just numbers, they are time capsules. The photons hitting Webb's detectors left that distant planet decades ago, carrying the story of its skies, oceans, and atmosphere across the void. Every measurement is a snapshot of a past moment in that world's life. Life, if it exists there, has been ongoing without our knowledge, independent of us, evolving on its own terms, oblivious to humanity's gaze. For all we know, creatures, perhaps unimaginably alien, look back at their own skies and wonder if someone else is out there, pondering the same questions we have. This is where imagination becomes inseparable from science. As you listen, dim the lights, let the room fall into quietude. Feel the hum of your surroundings fade into the cosmic silence. We are about to embark on a journey to a world that, until today, existed only in the realm of theory, simulations, and whispered speculation. The planet has no name yet, no entry in the catalogues of astronomy, no history written down. Yet it carries a profound significance, a mirror reflecting the possibilities of life itself. Imagine stepping onto its shores. The air is breathable, perhaps warm, perhaps carrying scents entirely alien. Water laps at a coastline formed over millennia, mountains rising where continents drift and collide, oceans shifting with tides unknown to Earth. Life here is not human. It is a story told in cells, in chemical reactions, in invisible interactions that defy the limits of our imagination. And yet, thanks to Webb, we can read these stories from afar. We can infer their presence, their rhythms, their signatures, without ever touching a single grain of that alien soil. And this brings us to a subtle, almost poetic realization. For all our telescopes, our calculations, our probes, we are still listening to whispers, interpreting shadows. This planet, with its staggering 99.7% chance of life, is a testament to the ingenuity of human curiosity and the vastness of the universe. It reminds us that the cosmos is not empty. It reminds us that somewhere, life thrives, quietly, persistently, across the distance and time that separate stars from each other. Yet, as thrilling as this discovery is, it carries a weighty question. What does it mean for us? How do we, a species confined to one fragile planet, respond to the knowledge that life exists elsewhere? Does it humble us, inspire us, or frighten us? These are not questions for tomorrow. They are the questions we must confront now, in this quiet moment, with the knowledge that humanity has, for the first time, glimpsed a kindred spark across the galaxy. Before we move forward, consider the telescope itself. Webb is more than a machine. It is a bridge across space and time. Its sensors translate invisible radiation into readable data. Its mirrors catch light older than most human civilizations, and its instruments allow us to detect molecules that hint at the most profound truth. Life is not unique to Earth. This is the new frontier, not merely observing stars and planets, but peering into the very chemistry of distant worlds, searching for the signature of existence itself. The implications ripple outward. This discovery will affect how we think about our place in the universe, how we search for other worlds, and how we imagine life beyond our cradle. Children born today will grow up knowing that life almost certainly exists somewhere else, and they may never feel the same existential loneliness that has colored humanity for millennia. Scientists will refine their models, astronomers will point telescopes, and theoreticians will debate endlessly, but the underlying truth remains breathtaking. The universe is alive, not metaphorically but literally. Somewhere, life dances in the oceans of another planet, oblivious to us, yet leaving traces that a telescope billions of kilometers away can detect. And so, as we prepare to delve deeper into this story, pause for a moment. Picture the vast distance separating us from that world, the journey of light that brings its message to our instruments, and the astonishing odds that we are witnessing this moment. Consider the meticulous work of scientists analyzing spectra, modeling atmospheres, ruling out false positives, and ultimately arriving at a figure that seems almost unbelievable. 99.7% probability of life. It is a number that will echo in textbooks, classrooms, and the minds of all who hear it for generations to come. Tonight, as we begin our journey, imagine standing on the edge of this new discovery. Imagine the thrill, the awe, and the quiet reverence of knowing that somewhere out there, life thrives. The universe, in all its vastness, has extended a hand across light years, and for the first time, humanity has grasped it, if only in understanding. And as we step further into this tale, we will uncover not just the science behind this extraordinary probability, but the stories, the questions, and the implications that arise when we truly accept that we are not alone. Welcome, then, to the first chapter of a cosmic revelation. The James Webb Space Telescope has found a world that may harbor life, and we are witnessing it in real time at the very edge of human understanding. What will we discover next? How will this change everything we thought we knew about life, the universe, and our fragile, beautiful place within it? The journey has only just begun. Imagine a telescope unlike any humanity has ever built. Not a simple lens or mirror perched on a mountaintop, but a marvel of engineering, a golden eye in the darkness of space. The James Webb Space Telescope is that eye, drifting silently 1 million miles from Earth in a place called the Second Lagrange Point, or L2, a region where the delicate balance of gravity allows it to float almost motionless relative to our planet and the Sun. It is the culmination of decades of dreams, failures, and meticulous planning, a machine designed not to see planets like ours directly, but to detect the faintest hints of their atmospheres, their temperatures, and their very chemical makeup. Webb is no ordinary telescope. Its mirrors are not glass but ultra-lightweight beryllium, coated in gold to capture infrared light. Infrared, just beyond the visible spectrum, lets Webb peer through dust clouds, see heat patterns, and detect molecules that would otherwise remain invisible. Every star, every planet, every distant galaxy emits light in ways that are a fingerprint of its composition and history. By collecting and dissecting this light, Webb can reveal secrets that have traveled across the galaxy for millions of years, secrets no human eye could ever perceive. But the telescope's brilliance is not just in its instruments, it is in the way it listens. Unlike older telescopes that relied on visible light, Webb hears the universe in the language of heat, the infrared whispers of atoms and molecules. In those whispers lie clues about water vapor clinging to distant planets, about methane and carbon dioxide dancing in alien skies, about oxygen, a gas that, on Earth, is almost synonymous with life. Infrared light is a cosmic messenger, carrying stories of worlds long before they could be seen directly, and Webb is the interpreter, translating those messages into human knowledge. Think about the scale for a moment. The telescope's mirrors are 21 feet across, 7 times larger than Hubble's. They are folded to fit inside a rocket, then unfurl like a golden flower in the emptiness of space. Every piece of Webb's engineering was designed to withstand conditions that would destroy ordinary instruments. Freezing cold, micrometeoroid impacts, and the complete vacuum of space. Its sunshield, the size of a tennis court, protects it from the sun's heat, keeping the instruments at temperatures near absolute zero, essential for detecting the faintest infrared signals. Webb is not just observing, it is dissecting. Every photon that reaches its sensors is recorded, analyzed, and categorized. Its spectrographs break light into hundreds of thousands of components, revealing the chemical composition of the sources it observes. This is how scientists can detect the fingerprint of oxygen or methane in an atmosphere hundreds of light years away, molecules that hint at processes that may be biological. And yet, despite all this technology, Webb is only as good as the questions we ask it. Pointing a telescope at a star is easy. Asking it to reveal the hidden chemistry of an exoplanet's atmosphere requires foresight, theory, and patience. Scientists must calculate where the planet passes in front of its star, when the starlight will filter through its atmosphere, and how to differentiate the planet's signal from the star's overwhelming glare. It is a cosmic puzzle, a dance of shadows and light, and only with precision, can we hope to extract the whispers of life from the cacophony of the universe. Now imagine the team of astronomers behind Webb. They are not just engineers and physicists, they are detectives, translators, dreamers. Each dataset is a mystery waiting to be solved. They comb through spectra, looking for anomalies, searching for patterns that match known chemical signatures, and discarding noise caused by cosmic rays, sensor errors, or interstellar dust. Every potential detection is scrutinized, modeled, and reanalyzed. The discovery of a planet with a 99.7% chance of life did not happen in a moment. It is the result of countless hours of preparation, calibration, and intellectual labor. Webb's design is itself a story of human perseverance. The telescope faced delays, budget crises, and engineering nightmares. Mirrors had to be polished to nanometer precision. Every mechanical part had to unfold perfectly in space, thousands of miles from the nearest human hand. Scientists and engineers simulated failure after failure, knowing that once Webb launched, no one could fix it. And yet, on that momentous day, the sunshield deployed flawlessly, the mirrors unfolded, and the telescope began to see in a way no machine before it ever had. But what does it mean to see in this way? To observe a distant planet, we do not receive images of continents or oceans. Instead, we measure starlight filtered through the atmosphere during a transit. When the planet passes in front of its star, a tiny fraction of the star's light passes through the gaseous envelope surrounding the planet. Molecules in the atmosphere absorb specific wavelengths, creating patterns, dark lines in the spectrum that tell us what gases are present. Water absorbs at certain infrared wavelengths, oxygen at others, methane at still another. It is like listening to a song and identifying each instrument not by sight, but by sound. This method, called transmission spectroscopy, is delicate and difficult. The signal is faint, sometimes drowned in the star's own activity. But with Webb, the faintest variations can be measured with extraordinary precision. And it was using this technique that the telescope detected the chemical fingerprints on the newly discovered planet. The combination of water, oxygen, and methane in the right proportions is not easily explained by natural processes alone. These gases react with each other and should cancel out over time unless continuously replenished. On Earth, that replenishment comes from life. Could it be the same here, on a planet hundreds of light years away? Webb's data suggest it almost certainly is. The implications are staggering. Consider the philosophical weight of this realization. A machine, an object of human creation, orbiting 1 million miles away, has detected the chemical signatures of life on another world. It is a triumph, not only of technology, but of imagination. It forces us to reconsider our place in the cosmos. We are not simply observers, we are participants in a universe brimming with possibilities. Webb has not merely extended our vision, it has expanded our consciousness. And yet, the telescope also reminds us of the fragility of knowledge. Every observation requires interpretation. Every signal a careful distinction between biological and abiotic sources. A volcanic eruption could mimic methane production. Ultraviolet radiation could split molecules and create false positives. Scientists must consider every possibility, rule out every alternative, and remain rigorously skeptical. Webb is a window, yes, but the story it tells must be read carefully. Even the act of discovery is collaborative. Scientists across continents analyze the data, cross-check results, and debate interpretations. The 99.7% probability is not a single declaration, but the convergence of independent analyses, statistical modeling, and simulations. It is humanity working together across time zones, disciplines, and cultures to answer one of the most profound questions ever posed. Are we alone? Beyond the science, Webb represents a bridge to imagination. Its discoveries inspire storytellers, philosophers, and dreamers to envision life beyond Earth in new ways. It allows us to speculate with rigor. What forms could this life take? How would it interact with its environment? What lessons does its existence hold for us? In this sense, the telescope is both a scientific instrument and a mirror, reflecting our curiosity, our hope, and our insatiable desire to know the universe and our place within it. And yet, for all its brilliance, Webb is only the beginning. This discovery, a planet with an extraordinary probability of hosting life, is a single note in a symphony that spans the galaxy. Webb will continue to observe, to catalogue, to analyze, revealing more worlds, more atmospheres, more signs that life may be common, diverse, and astonishingly resilient. Every new detection challenges assumptions, refines models, and deepens the mystery. For now, pause and imagine the telescope itself, floating in perfect silence, untethered except by the invisible threads of gravity, observing worlds we can scarcely comprehend. Every photon it catches is a story, every spectral line, a sentence, every dataset a chapter in a book written in light and chemistry. And through this instrument, humanity has glimpsed something profound, the unmistakable whisper of life on a distant planet. As we continue our journey, we will delve deeper into that world itself, its atmosphere, its chemistry, its potential biospheres, and explore what it means for life beyond Earth. But before we do, take a moment to appreciate the telescope that made it possible. The James Webb Space Telescope is not just hardware. It is a testament to human ingenuity, perseverance, and imagination. Without it, this discovery would remain a dream, a possibility, a what-if. With it, the universe has spoken, and we have listened. Now, imagine a world orbiting a distant star, far beyond our solar system, hidden in the inky depths of the Milky Way. A world that, until recently, existed only in theoretical models, computer simulations, and the faintest hints of starlight. It is not a cold, lifeless rock, nor a fiery gas giant. This is a planet that, against astronomical odds, seems to tick every box for habitability, a rare jewel among billions of worlds. Scientists have given it a designation, a string of letters and numbers that sounds clinical, almost sterile. Yet behind those characters lies a story far more thrilling than anything in the pages of fiction. A story of a planet that, according to Webb's instruments, carries the fingerprints of life with 99.7% probability. From Earth, it is impossible to see this planet directly with the naked eye. It is hundreds of light years away, a tiny point of light swallowed in the glow of its parent star. But when Webb turned its infrared gaze toward this world, something remarkable happened. The starlight passing through the planet's atmosphere revealed patterns that no natural process could easily explain. Water vapor, oxygen, and methane, all present in proportions that suggest active biological cycles, interacting in a delicate balance that hints at ongoing life. On Earth, such a combination is maintained by the web of life itself. Could it be the same here, across the vast gulf of space? Consider the star this planet orbits. It is not a raging giant, nor a dying ember. It is a stable, middle-aged star, providing just the right amount of energy to its planet. In cosmic terms, this is the sweet spot for life. Not too hot, not too cold, allowing liquid water to persist for billions of years. The planet's orbit is nearly circular, meaning it does not swing too close or too far from its star, avoiding extreme temperature swings. Its day-night cycle, while unknown in exact duration, is likely regular, offering predictable patterns that life, if it exists, could adapt to. But habitability is more than just orbit and water. Webb's spectrographs tell us about the composition of the atmosphere, the gases swirling above the planet's surface. Here, the results are extraordinary. Oxygen, a reactive gas that would otherwise be consumed in chemical reactions with rocks and minerals, persists in large amounts. Methane appears alongside it, a molecule that reacts quickly with oxygen, meaning that both gases must be replenished continuously. On Earth, that replenishment comes almost entirely from living organisms, plants, microbes, and animals participating in a vast cycle of life. The implication is staggering. The chemistry of this planet suggests not only that life could exist, but that it almost certainly does. Now pause to reflect on probability. In the vast expanse of the galaxy, planets are common, but truly habitable ones are rare. The combination of a stable star, the right orbital distance, liquid water, and a protective atmosphere is statistically unlikely. To find a planet that not only meets these conditions, but also shows chemical evidence of life is like drawing the winning lottery numbers, again and again. This is why scientists are speaking of a 99.7% chance. It is not a casual estimate, it is a calculated probability based on multiple overlapping signals refined through decades of planetary science and atmospheric modeling. The planet's potential biosphere invites both imagination and caution. We cannot yet know if it hosts vast oceans teeming with microscopic organisms, forests of alien flora, or even complex multicellular life. Its climate, weather patterns, and surface conditions remain mysterious. Perhaps it has seasons, storms, and tectonic activity like Earth, shaping its surface and recycling nutrients. Or perhaps it is a calmer world, with slow, steady cycles that support stable, microbial ecosystems. Every possibility challenges us to expand our definitions of life and reconsider how life might adapt to alien environments. One particularly fascinating aspect is the planet's potential for extremophiles, organisms that thrive in conditions that would be hostile or lethal on Earth. Webb's detection of methane alongside oxygen hints that life may not be confined to the surface. It could exist beneath oceans, inside rocks, or within atmospheres themselves, where chemical energy, rather than sunlight, drives biological processes. If so, this planet could host ecosystems entirely unlike anything we know, yet sustaining life with the same fundamental chemistry that has allowed organisms to flourish on Earth. And yet, for all its promise, this planet also confronts us with humility. We are looking at it across hundreds of light years, meaning the light Webb observes left that world centuries ago. What we detect is history, not present reality. Perhaps life thrived there when that light began its journey, only to face extinction in the meantime. Perhaps the 99.7% probability is the echo of a biosphere already lost, a ghostly signature preserved in starlight. Webb gives us the tools to ask questions, but the universe answers in whispers, not certainties. The planet also invites reflection on scale and perspective. To detect these atmospheric signatures, Webb relies on infinitesimal variations in starlight, changes measured in parts per million. The amount of light absorbed by water or methane is tiny, yet detectable across unimaginable distances. This is a testament not only to the sensitivity of human-made instruments, but also to the power of careful observation, statistical rigor, and decades of theoretical groundwork. The discovery is a triumph of human ingenuity, revealing something profound about life's potential to emerge and persist, even in a cosmos vast beyond comprehension. Scientists now face the next challenge: understanding the planet's environment in more detail. Future observations aim to detect additional molecules, estimate surface temperatures, and even search for seasonal changes that might indicate dynamic ecosystems. Each new dataset could confirm life's presence, reveal its complexity, or challenge current assumptions. The process is painstaking and deliberate, a slow unfolding of discovery that mirrors the patient work of archaeologists, uncovering traces of long-lost civilizations on Earth. This planet also holds philosophical significance. The implications of life beyond our solar system cannot be overstated. It challenges anthropocentric views, forcing humanity to consider itself not the pinnacle of existence, but one branch on a tree that may extend across the galaxy. It sparks questions about communication, morality, and destiny. If life is abundant, how do we define intelligence? If life is rare, what responsibility do we have to preserve it, both on Earth and elsewhere? Webb's discovery transforms these questions from abstract speculation into tangible inquiry. The planet's potential biosphere also rekindles wonder. Imagine the microscopic life forms floating in its atmosphere, consuming energy, reproducing, evolving over eons. Consider the possibility of oceanic organisms, perhaps analogous to plankton or corals, forming complex food webs that sustain larger creatures. Imagine life forms that use chemistry, rather than sunlight, as a primary energy source. All of these possibilities are consistent with the signals Webb has detected, yet all remain speculative until further observations confirm them. Finally, the planet reminds us of our limitations and our responsibilities. We have not yet sent probes, we have not touched its surface, and we may never be able to do so in our lifetimes. What we have is an understanding mediated through light, chemistry, and inference. Yet even without direct contact, the implications are profound. Life exists elsewhere. Life is not confined to Earth. The discovery expands our understanding of biology, chemistry, and the conditions under which life emerges. It challenges scientists to rethink models of planetary habitability, to refine simulations, and to explore the delicate interplay of physics, chemistry, and biology on worlds beyond our own. As we contemplate this distant world, two truths become apparent. One, the universe is capable of producing life in ways that parallel and perhaps exceed what we see on Earth. Two, our understanding is still in its infancy. Webb has given us a glimpse, a hint, a promise, but the full story of this planet, its ecosystems, and its potential civilizations, if they exist, remains to be written. And so, as we continue our journey, we step closer to the most exhilarating and unsettling question of all. What form does life take on this planet? How does it interact with its environment? What can it tell us about ourselves, our origins, and the possibilities of life across the cosmos? In the next section, we will delve into the chemistry of this extraordinary world, explore the molecules that hint at biology, and uncover why these signals have scientists around the globe holding their breath. The moment we speak of life, we often picture sprawling forests, oceans teeming with fish, or perhaps a bustling city humming with activity. But for James Webb, for the astronomers peering across hundreds of light years, life is not visible in that sense. It is chemical. It is the invisible molecular signature left in the air, in the dance of atoms, in the subtle absorption and emission of light as starlight filters through a planet's atmosphere. These are the fingerprints of life, and Webb has revealed them in astonishing detail on this distant world. Imagine for a moment the journey of a photon, a particle of starlight. It begins in the heart of a star, born of nuclear fusion, and travels for hundreds of years through the emptiness of space. It finally arrives at the planet, where it interacts with the atmosphere. Some of its energy is absorbed by molecules, which then vibrate, rotate, or change in ways unique to their chemical identity. The light continues on, carrying within it a map of the planet's atmospheric composition, an imprint of the molecules it has encountered. Webb captures this light, separates it into a spectrum, and reads it as one would read the rings of a tree or the layers of sediment in an ancient lake. The spectrum reveals something extraordinary. Water vapor. Not just a trace, but abundant water, swirling invisibly above clouds, oceans, and perhaps even glaciers. Water is life's universal solvent, the medium in which chemical reactions proceed with elegant efficiency. Its presence alone does not guarantee life, but it is a prerequisite. And here, it exists in quantities that suggest a dynamic hydrological cycle: rain, evaporation, condensation, all processes that can support life as we know it. Next, oxygen. On Earth, oxygen is rarely abundant in an atmosphere without life. It is reactive, quick to bind with rocks and metals, to combine with other molecules and vanish. Its persistence requires constant replenishment. On this distant planet, oxygen is present in quantities that hint at ongoing production. Could it be photosynthesis, or some other alien process we cannot yet imagine? Whatever the mechanism, its very presence, alongside other gases, is a powerful clue. Then there is methane. This gas is volatile, short-lived, and easily destroyed in oxygen-rich atmospheres. On Earth, Most methane comes from life, microbes in soil, wetlands, and the digestive tracts of animals. Its detection here, coexisting with oxygen, is nothing short of miraculous in terms of probability. In chemistry, these two gases should not coexist for long unless something actively replenishes them. Life is the most plausible explanation, yet the story does not end there. Webb's instruments have detected traces of carbon dioxide, perhaps in the right balance to support a greenhouse effect, keeping the planet warm enough for liquid water. The spectral lines suggest possible nitrates, molecules that on Earth are part of the nitrogen cycle, cycling between atmosphere, soil, and life. The interplay of these gases paints a picture not just of habitability, but of activity, a dynamic, evolving biosphere. Consider the odds. In billions of planets, only a fraction will orbit stars with the right stability. Only a fraction will lie in the habitable zone. Only a fraction will retain an atmosphere long enough for complex chemistry to develop. And within that tiny subset, the alignment of gases detected here, a delicate, chemically unstable equilibrium, is astronomically rare. This is why the chance of life is estimated at 99.7%. It is not speculation. It is inference based on overlapping, independently verified signals. The numbers are as close to certainty as we can reach without touching the planet. But understanding these chemical fingerprints requires careful thought. Life is not a single molecule or a single signal. It is the balance of many signals, the context, the ratios, the interactions. Oxygen alone might be explained by a non-biological process, such as photodissociation of water by ultraviolet light. Methane alone could come from volcanic activity or hydrothermal vents. But the co-occurrence of multiple gases, in the ratios observed, is extraordinarily unlikely to be natural. Webb allows us to read these ratios like words on a page, telling a story of chemistry shaped by biology. The detection of these molecules is a triumph not just of engineering, but of human curiosity and persistence. To measure such faint signatures across light years, astronomers must account for every confounding factor: the flicker of the star itself, cosmic dust between the star and the telescope, instrumental noise, even the Earth's own motion. They must separate what is truly planetary from what is stellar or interstellar. The result is a spectrum so precise it can distinguish between oxygen and ozone, methane and ethane, water vapor and carbon monoxide. Each spectral line is a breadcrumb, leading us deeper into the mystery of life on another world. Yet, as extraordinary as this is, it also raises profound questions. What form does life take? Is it microbial, floating in oceans, cycling chemicals without awareness or intent? Or is it multicellular, perhaps forming ecosystems as complex as Earth's? Does it use DNA or something completely different? We cannot answer these questions directly, but the chemistry hints at processes, at cycles, at metabolism, the hallmarks of life. Consider Earth's biosphere as a model. Oxygen production comes primarily from photosynthetic organisms. Methane comes from both geological and biological sources. Water cycles through evaporation, condensation, and precipitation. Nitrogen cycles through fixation, nitrification, and denitrification. On this distant planet, a similar interplay may be occurring, though its chemistry might follow rules unfamiliar to us. The same laws of physics and chemistry apply, but the exact pathways could be alien. Perhaps photosynthesis uses infrared light instead of visible. Perhaps methane is produced by entirely novel biochemical mechanisms. The possibilities stretch imagination, yet the basic principles of energy transfer, chemical cycling, and molecular interaction remain universal. Webb's findings also remind us of the patience of science. Detecting these molecules did not happen overnight. It required decades of theoretical modeling, of predicting what life's signatures might look like from afar. It required building a telescope of unprecedented precision, launching it into orbit, and calibrating it against known standards. It required teams of astronomers, chemists, planetary scientists, and engineers working together, interpreting data with statistical rigor, and publishing results that would withstand scrutiny. In other words, what we are seeing is the culmination of generations of human effort, all converging on the question, are we alone? There is a beauty in how subtle these signals are. They are not obvious, screaming evidence. They are delicate, requiring careful interpretation. The universe whispers rather than shouts, and only with the right instruments and the right questions can we understand its language. Each spectral line is like a note in a symphony, and when combined, they create a melody that hints at life. Webb is the conductor, translating these faint harmonies into meaning. But there is also a humility here. We are observers from afar, interpreting light that has traveled centuries to reach us. We cannot yet probe the oceans, taste the air, or see life with our own eyes. There may be confounding factors we have not considered. There may be unknown geochemical processes capable of producing similar signals. Yet the probability, the convergence of multiple independent lines of evidence, makes this planet unlike anything we have ever seen. It is not just another exoplanet, it is a world that beckons with the possibility that life exists beyond Earth. As we reflect on these chemical fingerprints, we are also forced to consider our own place in the cosmos. Life is not a unique miracle confined to one world. It may be resilient, adaptable, and perhaps inevitable when conditions align. The same laws of chemistry that drive life on Earth operate here, across the vast expanse of space. This planet is a testament to the universality of physics and chemistry, and perhaps to the universality of life itself. Finally, the chemical signatures detected by Webb are not just evidence. They are a call to further exploration. They inspire missions, instruments, and theories designed to test and refine our understanding. They demand patience, careful analysis, and imagination. They remind us that science is a journey, a process of discovery that unfolds over decades, generations, and perhaps even centuries. The molecules are there, waiting to tell their story. It is up to us to listen carefully, interpret wisely, and remain open to what we might learn. So far, we've looked at the invisible signatures of life, the gases, the molecules, the spectral whispers that hint at something alive. But now, let's imagine what that life might actually look like. This is where imagination meets science, where chemistry becomes ecology, and where we begin to picture entire alien ecosystems thriving under alien skies. First, consider the star this planet orbits. Its light sets the rhythm of life, the wavelength that fuels photosynthesis, the cycles of day and night that shape behavior. If it is a red dwarf, as many of the most promising habitable zone planets orbit, then the light is dimmer, redder, and more consistent than our Sun. On Earth, chlorophyll evolved to absorb the blue and red parts of the spectrum. On this planet, life may have evolved pigments tuned to infrared light. Forests, if forests exist, might not be green. They might shimmer in deep purples or blacks, reflecting and absorbing light in ways optimized for survival. Every leaf, every filament of algae, every photosynthetic microbe could be a masterpiece of adaptation, shaped by light no human eye has ever seen. Now consider gravity. If the planet is slightly larger than Earth, gravity could be stronger, influencing everything from the size of organisms to the architecture of their ecosystems. Trees may be shorter, stockier, and wider, with roots like sprawling networks of living bridges to stabilize them. Animals, if they exist, might crawl rather than leap, or evolve extraordinary muscular systems to compensate. Wings, if present, would need to be broader, membranes or feathers engineered to push against a heavier pull. Life adapts to physics with relentless precision, finding niches and exploiting them in ways both beautiful and alien. Then there's the atmosphere. Oxygen and methane are dancing together in precarious balance. What does that mean for life? Organisms could have evolved to utilize these gases in metabolism. Maybe there are creatures that breathe methane, converting it into energy while exhaling more complex hydrocarbons. Perhaps there are others that feed on oxygen-rich compounds, generating chemical byproducts that sustain entire microbial communities. The air itself could be alive with invisible networks of metabolism, microbes forming aerial ecosystems that drift like clouds, interacting in ways we are only beginning to imagine. Water, abundant and dynamic, is the stage upon which life performs. Oceans may be deep, dark, and full of strange currents. If life has arisen there, it may be entirely unlike fish or cephalopods. Bioluminescent organisms might dominate the twilight layers, producing light not for aesthetic beauty, but for communication, predation, or mating rituals. Currents may carry nutrients across vast distances, allowing microbial mats to thrive, giving rise to enormous blooms of life that could rival Earth's Great Barrier Reef in scale and complexity. And if there are continents, freshwater lakes, or ice-capped poles, each of these regions could host distinct ecosystems. With organisms adapted to extremes, we struggle to survive ourselves. Then consider evolution. On Earth, life evolves through competition and cooperation, mutation and natural selection. On this planet, evolution has had millions, perhaps billions of years to experiment under different conditions. Creatures might combine traits we would never expect, a plant that moves like an animal to seek sunlight, or an animal that photosynthesizes like a plant to supplement its diet. Symbiotic relationships could dominate, entire ecosystems dependent on the metabolic cycles of others, forming vast chains of interdependence that balance the planet's chemistry in ways that are detectable from space. If life exists on land, the terrain itself may be a testament to biology. Perhaps organisms secrete minerals or chemicals that alter soil composition, shaping mountains, valleys, or deserts. Forests could create microclimates, regulating temperature and humidity, influencing atmospheric circulation. Every breath of air, every drop of rain, every shifting wind could be shaped by the presence of life. A planetary-scale fingerprint of biology writ large across the surface. The microbial world may dominate in ways humans rarely appreciate. On Earth, microbes are invisible engineers of ecosystems, cycling nutrients, decomposing matter, and sustaining higher forms of life. On this alien planet, they could form vast mats in oceans, lakes, or moist soil, acting as keystone species in ways visible only from Webb's spectral data. They may be responsible for the chemical imbalances we detect, producing methane, oxygen, or other gases as byproducts of life, feeding into the global atmosphere in a subtle, yet measurable dance. Imagine predator and prey dynamics. Even without humans to imagine them, evolution tends to generate competition. On land or in the oceans, organisms may develop eyes tuned to infrared, echolocation to navigate murky waters, or chemical detection to hunt in dense vegetation. There may be predators that glide silently through the air or water, their senses exquisitely attuned to the slightest movement or chemical change. Prey species may evolve armor, camouflage, or symbiotic relationships with microbes that make them less palatable. The planet could be teeming with interactions invisible from orbit, yet encoded in the chemical balance of the atmosphere. And what of intelligence? Could there be sentient beings? This is where speculation becomes especially tantalizing. While the presence of life does not guarantee intelligence, the co-occurrence of chemical signatures hints at long-term planetary stability, a factor that can support complex life. Perhaps there are species capable of manipulating their environment, shaping ecosystems deliberately, leaving traces that Webb or future telescopes might detect as unusual landforms, chemical imprints, or artificial light. Even without cities or technology, such intelligence could influence planetary chemistry, creating patterns distinct from purely natural processes. Seasonal changes might also be detectable. On Earth, forests turn colors, oceans cycle nutrients, polar ice expands and contracts. On this planet, similar cycles could create fluctuations in gas concentrations, patterns of light reflection, or temperature variations observable across years. By measuring these changes, astronomers can infer not just the presence of life, but its activity over time, growing, reproducing, consuming, and interacting with its environment in ways consistent with biology. Consider too, extremophiles. Life on Earth thrives in boiling vents, acidic lakes, deep ice, and radioactive soils. On this planet, organisms could inhabit extreme niches that push our definitions of habitability. Life may flourish beneath thick ice caps, in subsurface oceans, or in chemically harsh environments, contributing to atmospheric chemistry only indirectly through the gases they release or the minerals they process. What seems inhospitable at first glance may, in fact, be teeming with alien biology. Finally, think about connectivity. Ecosystems are networks, not isolated pockets. Microbes influence plants, plants influence animals, animals influence microbes. Atmospheric composition is the summation of countless metabolic interactions. Ocean currents distribute nutrients, weather patterns carry spores, and chemical cycles link continents and oceans. The alien planet, in this view, is not a barren rock or a simple globe of water. It is a complex, living system, interconnected and dynamic, responding to the rhythms of its star and the needs of its inhabitants. Webb has given us a glimpse into this world. Not a photograph, not a map, not a direct encounter, but a spectral fingerprint that suggests life is present and active. From that, we can extrapolate a picture of alien ecosystems, alien forests, alien oceans, alien skies, alive with chemistry, movement, and perhaps intelligence. Each molecule detected, each absorption line, each subtle variance in the spectrum is a window into a vast, unseen biosphere, hinting at creatures, plants, microbes, and systems that have never been observed by human eyes. The challenge now is both scientific and philosophical. How do we move from chemical signatures to understanding ecosystems? How do we imagine life forms that obey the same laws of chemistry and physics, but express them in utterly alien ways? How do we measure activity, complexity, and interdependence from across light years? These questions push the boundaries of biology, chemistry, planetary science, and imagination itself. And yet, even without knowing specifics, the implications are staggering. This planet is a reminder that life is not confined to Earth. It is a proof of principle that, given the right conditions, chemistry organizes into life, ecosystems emerge, and planets become living worlds. It tells us that life may be resilient, adaptable, and abundant, hiding in plain sight among the stars. As we stand on the cusp of this discovery, we must also confront our own expectations. Alien ecosystems may not mirror our own. Life may not be friendly, intelligent, or even recognizable. It may operate on timescales, chemistries, and strategies beyond our comprehension. Yet, by studying their signatures, we learn not only about them, but about the universal principles that give rise to life anywhere. We will dive into the technological marvels that allowed James Webb to detect these signs, the instruments, methods, and engineering feats that transform faint starlight into a cosmic fingerprint of life. How did humans, from 93 million miles away, reach across space to confirm the possibility of life on another world? The story of discovery is inseparable from the story of the planet itself. So, we've imagined the alien ecosystems, the strange forests, oceans, and skies alive with life. But now comes the part where human ingenuity bridges the vast void of space. How did we, from a tiny blue planet orbiting an ordinary star, reach across light years to detect the faintest hints of life on a distant world? The answer lies in James Webb's instruments, in physics, chemistry, and decades of planning, all coming together to turn photons from a star into a story of life. James Webb Space Telescope, or Webb for short, is not just a telescope. It is a time machine, a chemist, and a detective rolled into one. Unlike the Hubble Space Telescope, which focused primarily on visible light, Webb is designed to observe in infrared. Why infrared? Because when you look at a planet hundreds of light years away, the star it orbits overwhelms most of the light. Visible light is bright, blinding, and makes it nearly impossible to see a tiny world next to it. Infrared light, however, lets us detect the heat signatures of planets, the subtle differences between what the star emits and what the planet itself absorbs and re-emits. It's a trick of physics, exploiting the fact that warm objects, including planets with atmospheres, glow in infrared wavelengths. But infrared alone isn't enough. We need instruments capable of breaking light into its components, much like a prism splits sunlight into a rainbow. Webb carries several spectrographs, NER-spec, NER-cam, MIRI, that can analyze the light from a planet in exquisite detail. These instruments measure absorption lines, tiny dips in brightness at specific wavelengths caused by molecules in the planet's atmosphere absorbing light. Each molecule has a unique fingerprint. Water vapor absorbs here, carbon dioxide there, methane, ozone, oxygen, they all leave telltale marks. By reading these fingerprints, we can infer the chemical composition of the atmosphere without ever seeing the planet's surface directly. The first challenge is separating the planet's signal from the overwhelming brightness of its star. Imagine trying to spot a firefly next to a lighthouse from thousands of miles away. Webb overcomes this using coronagraphs, which block the star's light while letting the faint glow of the planet shine through. It's an elegant solution, essentially creating an artificial eclipse. Every photon that passes through the coronagraph carries information about the planet, its atmosphere, and perhaps its life. Then comes the method called transit spectroscopy. If the planet happens to pass directly in front of its star from our point of view, a transit, some of the starlight filters through the planet's atmosphere before reaching Webb. Molecules in the atmosphere absorb certain wavelengths, leaving subtle imprints in the light. By comparing the star's spectrum during the transit with the spectrum when the planet is elsewhere in its orbit, scientists can isolate these tiny differences and decode the atmospheric composition. It's a bit like reading a shadow of the atmosphere, a fingerprint left by gases interacting with starlight. Here's where the extraordinary skill of scientists comes in. The signals are faint, often buried in noise. Cosmic rays, instrumental vibrations, thermal fluctuations, and even dust in space can interfere. But careful calibration, repeated observations, and sophisticated algorithms allow researchers to pull the true signal from the background. Each dip and spike in the spectrum is analyzed, modeled, and compared against simulations to ensure that what we see isn't an artifact of the telescope itself. For this particular planet, the one with the astonishing 99.7% chance of life, Webb detected a combination of molecules that on Earth are strongly associated with biology. Methane, oxygen, and water vapor coexisting in the same atmosphere is not a random occurrence. On our planet, oxygen is highly reactive and would quickly disappear if not constantly replenished by photosynthesis. Methane too reacts with oxygen and has a short lifetime unless continuously produced. To find both together in a distant atmosphere hints strongly at an active, self-sustaining process, life. But Webb didn't stop at detecting gases. Its instruments can also measure temperature variations across the planet's surface and atmosphere. By analyzing the infrared light emitted from the day and night sides of the planet, scientists can infer atmospheric circulation, weather patterns, and even heat retention, factors that influence habitability. A planet with stagnant air might trap greenhouse gases, while a planet with dynamic winds and oceans can distribute heat and sustain diverse climates. The telescope's unprecedented sensitivity also allows for detection of minor compounds that may be critical for life. For example, trace amounts of phosphine, a gas that on Earth is primarily produced by microbes, or unusual sulfur compounds, can serve as biosignatures. By detecting these molecules, scientists gain insight into chemical processes that are difficult to explain through geology alone. It's a forensic investigation at a planetary scale. But Webb doesn't act alone. Its observations are cross-verified with theoretical models. Astrophysicists simulate countless scenarios, asking, could the detected molecules form abiotically through volcanic activity, cometary impacts, or chemical reactions in the atmosphere? If not, biology becomes the most plausible explanation. These models are complex, involving chemistry, physics, climate dynamics, and even planetary formation processes. It's a multidisciplinary effort, requiring expertise from every corner of science. Timing is another crucial factor. Observing transits requires patience, precision, and a bit of luck. Many exoplanets have long orbital periods, meaning they only pass in front of their stars every few months or years. Webb's observing schedule must anticipate these moments, sometimes waiting patiently for years to capture the fleeting alignment that reveals the planet's atmospheric secrets. Missing a single transit can mean waiting for an entire orbital period to try again. And there's the importance of redundancy. Multiple transits are observed to confirm the signal. Data from different instruments are compared, spectral lines are checked across wavelengths, and observations are repeated to rule out instrumental or cosmic anomalies. Only after rigorous validation do scientists declare a biosignature detection credible. This careful approach ensures that claims of life aren't premature or misleading. Webb's achievement also relies on its location. Orbiting the second Lagrange point, L2, about 1.5 million kilometers from Earth, the telescope enjoys a stable thermal environment, free from Earth's heat and light pollution. Its sunshield keeps instruments cold and prevents stray light from interfering with delicate measurements. In this frozen silence, Webb can detect the faintest infrared glimmers, turning them into stories about distant worlds. And yet, even with all this sophistication, uncertainty remains. Science doesn't leap to conclusions. The 99.7% chance is derived from probability models, combining chemical data, planetary conditions, stellar radiation, and comparisons with Earth. It reflects an overwhelming likelihood, but acknowledges the unknowns, unknown processes, unknown chemistries, and unknown forms of life that might confound our assumptions. This humility is part of Webb's power. It allows us to detect life without assuming we fully understand it. Finally, consider the human element. Decades of engineering, testing, launching, and calibrating culminate in each observation. Thousands of scientists, engineers, and technicians contributed to Webb's success. Every photon captured represents not just a signal from a distant planet, but the culmination of human ingenuity, patience, and collaboration. In that sense, detecting life on another world is as much a testament to us as to the life we discover. The instruments, the orbits, the spectroscopy, the models, all these pieces fit together to turn a faint spectral signature into a profound insight. A planet light years away may not be barren, it may be alive. And through Webb, we are seeing it for the first time, learning not just about molecules, but about ecosystems, climates, and perhaps even civilizations in their infancy. In the next section, we'll explore the implications of this discovery. What does it mean for humanity, for our understanding of life in the universe, and for the philosophical and societal questions that arise when we realize we are not alone? The science is incredible, but the consequences ripple far beyond the telescope, reaching into every corner of human thought. Imagine standing on a quiet night in your backyard, looking up at the stars, realizing that one of those distant points of light is not just a planet, but a world teeming with life. It's a revelation that shakes the very foundation of how we see ourselves. For centuries, humans have asked, are we alone? Are we special? Are we the pinnacle of life? A singular occurrence in the vast cosmos? Now, the James Webb Space Telescope suggests that the answer might be no. Not by a shadow of a chance, but by an almost certain 99.7% likelihood. Life exists elsewhere. The first, most immediate implication is philosophical. Humanity has long built its identity around the idea of being the sole conscious inhabitants of the universe. Religions, mythologies, and philosophies often frame humans as the center of creation, unique and singular. Learning that life exists on another planet, even microbial, even simple, forces a profound re-evaluation. We are no longer the solitary miracle. We are part of a cosmic community, linked to other living beings by the fundamental laws of chemistry, biology, and evolution. And yet, this knowledge is both exhilarating and humbling. The realization that life exists elsewhere diminishes our sense of cosmic arrogance, but expands our sense of wonder. Our place in the universe is not diminished, it is contextualized. Earth is not an anomaly, but one of many habitats capable of sustaining life. We are threads in a vast tapestry of biology, a story unfolding across countless worlds and countless epochs. This perspective changes how we think about stewardship, not just of our planet, but of life itself. If life can arise elsewhere, perhaps it is fragile, precious, and deserving of careful protection wherever it exists. There are also scientific implications that ripple across multiple disciplines. Astrobiology, once a field dominated by theory, suddenly has a data point, however preliminary, that validates its search. Evolutionary biology must grapple with a new comparison. If life exists on a distant planet, does it follow the same biochemical rules? Is DNA, or something functionally similar, universal? Or do these alien organisms employ an entirely different molecular machinery, challenging our assumptions about what life can be? Each of these questions opens up new research avenues, potentially revolutionizing biology. Then there's the question of technology and civilization. While the planet Webb observed may not yet have intelligent life, the existence of life increases the probability that intelligence could arise elsewhere. Our own technological civilization is incredibly brief in cosmic terms, barely a blink in geological time. Yet, if life is common, the emergence of intelligence somewhere becomes less improbable. That insight directly connects to the Fermi paradox, where is everybody? And suggests that perhaps intelligent civilizations exist, but are separated by vast distances or time spans. But beyond abstract science, there are practical consequences for humanity. Our knowledge of life elsewhere reframes exploration itself. Space travel, once a curiosity or ambition, now takes on urgency. We have proof that habitable, life-bearing worlds exist, and the next step is to understand them, interact responsibly, and perhaps one day, visit them. The concept of planetary protection becomes not just an academic concern, but a moral imperative. Introducing Earth life to alien ecosystems, or vice versa, carries risks we must contemplate carefully. Contamination is no longer a hypothetical, it's a responsibility. The discovery also challenges economics, politics, and global priorities. Imagine governments, agencies, and institutions absorbing this knowledge. Funding for space exploration may surge, not for abstract goals, but for the tangible possibility of studying or interacting with life elsewhere. Collaboration may become more than a diplomatic nicety. It may become essential. Humanity's future in the cosmos could require a unified approach, an unprecedented level of global coordination. If we are not alone, competition, secrecy, or short-term thinking may jeopardize not only scientific progress, but ethical responsibility. On a societal level, the psychological impact is profound. Humans are storytellers. Our myths, our literature, and our dreams are intertwined with our understanding of solitude in the universe. Learning that life exists elsewhere reshapes these narratives. Religious interpretations may evolve to accommodate extraterrestrial biology. Philosophical frameworks might shift from anthropocentric models to cosmic ecologies. Literature and media will inevitably explore new scenarios, from alien microbes reshaping medicine and agriculture to profound cultural dialogues about interplanetary ethics. Education, too, must adapt. Biology classes must begin to incorporate astrobiology. Chemistry, geology, and physics must connect to the broader question of life's universality. Students will learn not just about the diversity of life on Earth, but about the potential diversity of life across the stars. The imagination will stretch, inspiring new generations to pursue careers once considered science fiction. The very definition of natural sciences may expand to include comparative planetology and exobiology. Ethics becomes an urgent concern. If life is found elsewhere, what are our moral obligations? Are we allowed to interfere with an alien ecosystem, even accidentally? Should we seek to communicate, or should we observe quietly, minimizing disruption? Humanity's sense of responsibility, already stretched by environmental issues on Earth, suddenly extends to the stars. Decisions made today could echo for centuries, determining whether life elsewhere thrives, is disrupted, or vanishes without notice. Culturally, we may also see an awakening of global unity, or perhaps tension. The knowledge that we share the universe with life beyond Earth is a humbling equalizer. Borders, conflicts, and human divisions may feel smaller when measured against the backdrop of cosmic life. Yet, it could also spark competition. Who will lead in the exploration of life-bearing worlds? Who will claim the moral high ground in interacting with alien biology? Questions of jurisdiction, sovereignty, and ownership in space are no longer theoretical. They become immediate concerns in light of confirmed life. The discovery also reframes our understanding of the fragility and rarity of life. Even if life is widespread, intelligent or complex ecosystems may remain rare. Each biosphere we detect becomes a laboratory for understanding survival, adaptation, and resilience. It reminds us of the precariousness of our own civilization, which has survived only a few 100,000 years. If life can arise elsewhere, but intelligent life struggles to persist, then humanity's own survival gains a new urgency. Lessons learned from other worlds, if we can ever decode them, could be critical in preventing self-destruction. Finally, there is wonder, pure, unfiltered awe. Knowing that somewhere, light years away, organisms are thriving, adapting, perhaps even gazing at their own night skies, reshapes our sense of time and space. It encourages curiosity, drives imagination, and fosters humility. We are not alone, and in that realization, the universe becomes simultaneously larger, richer, and infinitely more mysterious. Our tiny species on a small blue planet is part of a vast, interwoven story of life, stretching across distances and epochs we can barely comprehend. We will explore the potential for communication and contact. What happens if life progresses beyond microbes? Could we ever send messages across light years? Could life elsewhere even detect us? The implications of discovering life extend far beyond science. They reach into philosophy, ethics, and the very way we understand our place in the cosmos. Imagine staring at the night sky, knowing that a distant planet almost certainly harbors life. Your mind races through the possibilities. Microbes, algae, or single-celled organisms may already exist there, quietly cycling nutrients in alien oceans or hidden beneath frozen crusts. But what if it's more than that? What if intelligence has arisen, curiosity has blossomed, and a civilization somewhere is asking the same questions we've been asking for millennia? Are we alone? Is there anyone else out there? The first challenge to this possibility is distance. Even if life has advanced on that planet, the vast cosmic gulf separating us is staggering. Communication, too, is limited by the speed of light. A radio signal sent today would take centuries to arrive, and any reply would take just as long. We are constrained by physics, not imagination. Yet the sheer existence of life opens doors to theoretical possibilities. Could we communicate, even indirectly? Scientists have proposed sending electromagnetic signals, radio waves, lasers, or even modulated light pulses, designed to be unmistakably artificial. These messages could include prime numbers, chemical formulas, or mathematical constants, universal patterns intelligible to any technologically advanced species. The hope is that intelligence recognizes patterns where nature would not produce them. A deliberate sequence, unlike chaotic natural emissions, becomes a cosmic calling card. But we also face profound challenges in interpretation. If life on that planet is microbial or fundamentally different in biochemistry, communication may be impossible. Even with intelligent life, cognition could diverge drastically from ours. Concepts we take for granted, time, space, mathematics, may be irrelevant or understood in ways we cannot fathom. Attempting to bridge that cognitive chasm is more than a matter of translation. It is a matter of empathy across species, across evolutionary history, and across entirely alien senses. Now, imagine the excitement of detecting the faint signature of a technologically active civilization. Strange radio emissions, laser pulses, or even signs of megastructures. Such a discovery would immediately shift the trajectory of human endeavor. Projects like SETI, Search for Extraterrestrial Intelligence, would become front-page science, backed not just by curiosity, but by evidence suggesting contact might be possible. Suddenly, listening for signals becomes urgent, not optional. Yet with opportunity comes caution. Contact with a civilization millions or billions of years ahead of us, or even only slightly advanced, could carry unforeseen consequences. History on Earth offers grim lessons. When technologically unequal societies meet, the results are rarely balanced or peaceful. Disease, exploitation, and domination often accompany contact. On a cosmic scale, the risks could be magnified. An advanced civilization might not even perceive us as sentient in the same way we perceive one another. Or perhaps they would actively avoid us, following a principle akin to the cosmic quarantine hypothesis. Intelligent life preserves itself by avoiding interference with younger civilizations. Another possibility is that life we detect is intelligent, but non-technological. Consider dolphins or octopuses on Earth, highly intelligent by biological standards, yet lacking technology capable of long-distance communication. On an alien world, intelligence could manifest in ways we cannot recognize. Complex social behaviors, problem-solving, or environmental manipulation might exist. But without structures that produce electromagnetic emissions, the civilization remains invisible to our instruments. The prospect of communication is not merely scientific, it is philosophical. If we find life capable of understanding us, what do we say? Do we assert our presence, proudly announcing our existence, or cautiously observe, respecting boundaries we barely comprehend? The questions extend beyond survival to ethics. Are we ready to meet a life form with its own history, culture, and potentially its own ethics? How do we ensure that contact is mutual, respectful, and non-destructive? There is also the concept of passive communication, the idea that life on our planet could be transmitting unknowingly. For thousands of years, Earth has broadcast its presence through radio and television waves, now reaching light years into space. Alien observers, if technologically advanced, could detect these emissions and deduce that a civilization exists here. In a sense, humanity has already sent a cosmic greeting, unintentional but undeniable. The implications are unsettling. If someone else out there has noticed, they may already be aware of us, long before we have found them. Then there's the potential for indirect communication through observation. Life elsewhere may leave signatures in its environment, terraforming efforts, atmospheric modifications, or chemical anomalies that indicate intelligence. These signs could act as messages in themselves, telling us that a species exists, thrives, and perhaps understands the universe in ways we might eventually decipher. It's a subtle form of contact, more about detection than conversation, yet no less profound. Another challenge is temporal mismatch. Civilizations might not overlap in time. Life could emerge, flourish, and vanish in epochs far removed from our own. The planet Webb observed may be in a stage analogous to Earth's pre-industrial age, or it could already be in decline. Even if life is present, we may be looking at the wrong moment in history. Interstellar communication requires synchrony, a cosmic alignment of curiosity and capability that may be rare. And yet, hope persists. Our scientific tools are evolving rapidly. The James Webb Telescope and its successors can detect biosignatures, chemical anomalies, and environmental conditions indicative of life. Future missions may refine these detections, identifying spectral lines, atmospheric imbalances, or unusual energy emissions. Each new discovery increases the probability that one day we will not just know that life exists, but interact with it in some meaningful way. The societal implications of potential communication are immense. A confirmed signal from an alien world would reshape politics, culture, and religion overnight. Humanity would face new questions. How do we present ourselves? Do we speak for all of Earth or acknowledge our fragmented nations? What do we offer as a representative of a species that has evolved in isolation? Philosophers, ethicists, and policymakers would suddenly occupy as critical a role as scientists, tasked with navigating the first steps of interstellar diplomacy. Finally, consider the psychological impact. Knowing that intelligent life might exist forces us to confront both our insignificance and our uniqueness. The realization is at once humbling and inspiring. Humbling because the universe is vast and life may be common. Inspiring because intelligence, creativity, and curiosity are shared qualities, binding us across space and time. It challenges us to think beyond survival, to imagine cooperation across worlds, to consider the possibility of a cosmic community in which knowledge, art, and culture extend far beyond Earth. Imagine the thrill of knowing that life almost certainly exists on a distant world. That knowledge sparks imagination, curiosity, and ambition. And yet, the universe is vast, the distances immense, and our current technology painfully limited. Reaching, observing, or interacting with that alien life is not merely a question of desire. It is a challenge that tests the boundaries of physics, engineering, and human perseverance. To truly grasp what it would take, we must step into a world where science meets audacity, where imagination is tethered to reality, and where every breakthrough builds on centuries of knowledge. The first hurdle is sheer distance. The planet Webb observed is hundreds of light years away. Even light, the fastest thing in the universe, takes centuries to travel that distance. For a spacecraft traveling at speeds attainable today, the journey could take thousands of years. To put this in perspective, the Voyager probes, launched in the 1970s, have traveled barely beyond the outer edges of our solar system. Even with incremental technological progress, interstellar travel is a challenge orders of magnitude beyond anything humanity has achieved. This limitation has sparked revolutionary ideas in propulsion. Concepts once confined to science fiction are now being seriously studied. One is the light sail, a spacecraft propelled by the pressure of photons from lasers or the sun. In theory, a small craft could accelerate to a significant fraction of the speed of light using focused laser arrays. Projects like Breakthrough Starshot aim to demonstrate this, potentially sending tiny probes to nearby stars within decades rather than millennia. But scaling this technology to carry instruments capable of life detection on distant planets remains a monumental challenge. Then there are fusion and antimatter engines, the stuff of both dreams and rigorous physics. Fusion, the process that powers the stars, could theoretically provide incredible thrust and efficiency, propelling ships across interstellar distances faster than any chemical rocket. Antimatter, matter's mirror image, releases energy with nearly 100% efficiency when annihilated with matter, offering the ultimate energy source for propulsion. Yet, both require technologies that are nascent or impractical with today's engineering capabilities. Containment, fuel generation, and safety concerns remain massive hurdles. Even if we manage propulsion, the next challenge is life detection across light years. We cannot simply land on the planet and take a soil sample, at least not yet. Our only tools are remote sensing, telescopes, and the interpretation of subtle signals in the light that reaches us. The James Webb Space Telescope has already opened a window into this domain, capable of analyzing exoplanet atmospheres for biosignatures, chemical compounds that suggest life, like oxygen, methane, or water vapor. But interpreting these signals is complex. Nature can produce similar signatures through volcanic activity, atmospheric chemistry, or non-biological processes. Disentangling the artificial from the natural requires precision, patience, and sophisticated modeling. Advances in spectroscopy, measuring how light interacts with matter, are central to this effort. Each molecule absorbs and emits light at specific wavelengths. By studying starlight that passes through a planet's atmosphere, scientists can detect tiny dips or spikes in certain wavelengths, revealing the chemical makeup of that atmosphere. It's as if the planet is sending a coded message hidden in the light, waiting for a careful observer to decode it. The level of precision required is staggering. Detecting a faint trace of methane amidst the overwhelming glow of a star demands instruments capable of sensing variations smaller than 0.01%. Then comes data analysis and interpretation, another colossal hurdle. Even with the best telescopes, signals are weak, noisy, and incomplete. Advanced algorithms, machine learning, and artificial intelligence are now essential. These systems sift through terabytes of data, identifying patterns that humans might miss. They separate cosmic interference from meaningful anomalies, flag potential biosignatures, and even predict what kinds of signals a distant civilization might produce. In a sense, AI becomes a partner in exploration, extending human perception across light years. Yet observing life is only part of the equation. Suppose we detect clear signs of intelligence, radio signals, laser pulses, or unusual atmospheric engineering. How do we respond? Direct communication introduces new technological hurdles. Conventional radio waves are limited by distance and dispersion. Laser communication offers higher bandwidth and focused energy, but aligning a beam across hundreds of light years with pinpoint accuracy is extraordinarily difficult. A misalignment of even a fraction of a degree could mean missing the target entirely. Moreover, sustainability becomes a factor. Maintaining observatories, laser arrays, and interstellar probes over decades or centuries demands long-term planning, political will, and uninterrupted funding. Science often progresses in fits and starts, but interstellar projects require vision spanning generations. The humans initiating these missions may never see results, yet they must design systems robust enough to operate autonomously, resilient against cosmic radiation, mechanical failure, and unforeseen anomalies. Then, there is the issue of energy requirements. Propelling a craft across light years, generating powerful lasers, or maintaining cryogenic instruments for centuries requires staggering amounts of energy. Harnessing this energy may demand innovations in nuclear fusion, solar power on an unprecedented scale, or tapping exotic sources we've only theorized about. Energy management isn't just a logistical challenge, it is the lifeblood of interstellar exploration. We must also consider survivability. Cosmic radiation, micrometeorites, and extreme temperatures threaten both instruments and humans. Any probe venturing far beyond the solar system must be shielded, autonomous, and capable of repairing itself, or at least enduring until it completes its mission. The longer the journey, the more robust the technology must be, essentially building spacecraft as living systems that can survive decades or centuries of isolation. Then there's the potential for quantum communication, a technology that could revolutionize interstellar messaging. Quantum entanglement allows correlated particles to instantaneously affect one another, even across great distances. While it does not allow faster-than-light information transfer under current physics, it might provide unhackable, highly secure communication channels, critical if we ever hope to interact with other intelligent species. This could open new possibilities for messages encoded in ways completely unlike our current electromagnetic transmissions. Another innovation on the horizon is swarm probes, inspired by both natural systems and advances in nanotechnology. Instead of sending a single, massive spacecraft, thousands of tiny probes could travel together, each carrying sensors, cameras, or communication devices. Swarms offer redundancy, adaptability, and distributed sensing, increasing the odds that at least some probes survive the long journey. They might operate cooperatively, sharing data in real time across light years, creating a networked exploration system reminiscent of an interstellar internet. Yet even as we imagine these possibilities, the universe reminds us of its scale. Communication delays measured in years or centuries, vast distances, and the sheer fragility of life impose humility. Every technology we conceive must contend with forces far beyond our control: stellar radiation, gravitational anomalies, interstellar dust, and cosmic expansion. Even the smallest miscalculation could render decades of effort fruitless. And still, humans innovate. We have built telescopes that detect planets hundreds of light years away, lasers that communicate across oceans, and spacecraft that have left the solar system entirely. Each advance shrinks the cosmic gap, turning theoretical dreams into plausible missions. Every new material, algorithm, or propulsion breakthrough becomes a step toward observing, interacting with, or even understanding alien life. Finally, consider the philosophical impact of these technological hurdles. Humanity is being forced to think on scales previously unimaginable. Planning decades, centuries, or even millennia into the future challenges our collective patience, our foresight, and our ability to collaborate across generations. The search for life is no longer just a question of curiosity. It is a test of endurance, vision, and imagination. It asks us to rise above the limitations of our era and imagine ourselves as part of a continuum that spans stars and centuries. Imagine standing beneath the night sky, staring into the darkness punctuated by distant stars. For millennia, humans have looked up and wondered if we are alone, if someone, or something, else peers back. Now, the James Webb Space Telescope has found a planet with a 99.7% chance of life. This isn't just a scientific milestone, it is a philosophical earthquake, shaking the foundations of what we believe about ourselves, our purpose, and our place in the cosmos. To understand the weight of this discovery, we must explore its implications for humanity, culture, religion, ethics, and even our long-term survival. First, consider the impact on human identity. For centuries, humans believed Earth was the center of all things, a perspective reinforced by religion, philosophy, and the limits of ancient astronomy. The Copernican revolution shattered that notion, placing the Sun, not Earth, at the center of our solar system. The discovery of exoplanets expanded this further, revealing that planets are common, and now we are on the verge of confirming life elsewhere. Humanity is no longer the sole focus of life in the universe. We are participants in a vast, interconnected cosmos, one where life can arise, flourish, and evolve under conditions far beyond our imagination. This shift reshapes philosophical thought. What does it mean to be human if life exists elsewhere? If extraterrestrial organisms are fundamentally different, do they challenge our definitions of intelligence, consciousness, and morality? Could life on that distant planet think, feel, or dream in ways we cannot even begin to comprehend? The realization that life is not unique forces us to reconsider long-held assumptions about value and meaning. We are no longer the lone narrative in a cosmic story. We are one chapter among many, and perhaps not even the first or most advanced. Then there is the profound ethical dimension. Humanity now faces a new responsibility: how to approach contact with life beyond Earth. If the planet Webb observed hosts complex organisms, or intelligent ones, what obligations do we have? Do we intervene, observe, or protect? The lessons of history caution us. Contact between civilizations at different levels of technology often leads to destruction, exploitation, or unintended consequences. Colonization on Earth's own continents has left scars that persist for centuries. How much more careful must we be with life that evolved independently across light years? This discovery also touches religion and spirituality. Many faiths have long held that life on Earth is unique, a special creation in a vast void. Learning that life exists elsewhere challenges these narratives, prompting reinterpretation of scripture, dogma, and belief systems. Some might see this as a threat, while others may perceive it as a confirmation of the universe's richness, the divine hand manifesting in forms far beyond human imagination. The theological debate alone could reshape global thought in profound ways. Consider also the impact on science and knowledge. Humanity's role shifts from isolated observer to cosmic participant. The methodologies of biology, astronomy, and planetary science must expand to account for forms of life radically different from our own. Life that evolved under different stars, different gravities, or different atmospheric chemistries challenges the universality of Earth-based assumptions. Biologists must ask, what is truly essential for life? How flexible is evolution? What chemical, physical, or biological laws allow organisms to thrive elsewhere? Each discovery pushes the boundaries of knowledge, forcing us to rewrite textbooks, rethink theories, and embrace the unexpected. Then comes the question of psychological and societal impact. Knowing that life exists elsewhere may alter human behavior, culture, and ambition. Will we feel smaller and insignificant, humbled by the vastness of the cosmos? Or will we feel empowered, inspired to reach beyond our planet, to explore, to communicate, to connect? Historically, major shifts in cosmic perspective, like the realization that Earth is not the universe's center, have driven human progress. The confirmation of extraterrestrial life could spark a renaissance of exploration, science, art, and philosophy. Another dimension is the existential reflection. If life is common, what is the purpose of intelligence? What drives civilizations to survive, to explore, to create? On that distant planet, life may have evolved for millions of years, navigating its own challenges, forming ecosystems, perhaps even developing intelligence. The realization that our existence is one possibility among countless others reframes the human experience. It asks us to consider what legacy we wish to leave, not just for ourselves, but for the universe at large. This ties directly to the Fermi paradox, which we explored in earlier sections. If life is so abundant, why haven't we yet seen evidence of other intelligent civilizations? The discovery of this planet suggests that life is not just probable, it exists. The silence, therefore, may not indicate loneliness, but distance, technological gaps, or deliberate concealment. Perhaps advanced civilizations become silent to survive, retreating into isolated habitats, or migrating to safer, more stable regions of space. For humanity, this discovery is both a clue and a warning. Life may be everywhere, but survival is precarious. The confirmation of life also forces reflection on long-term responsibility. Humanity has a choice. Will we continue as a species capable of creating destruction, or will we evolve towards stewardship and preservation? Knowing that life exists beyond Earth magnifies the stakes. We are not merely caretakers of our planet, but participants in a cosmic ecosystem that spans the stars. Our actions, pollution, climate change, nuclear weapons, or space exploration may affect not just Earth, but the broader tapestry of life. Awareness of extraterrestrial life invites a form of cosmic ethics, a code that extends beyond humanity and even beyond our solar system. Moreover, this discovery may inspire collaboration and unity. If life exists elsewhere, divisions based on nationality, religion, or culture may begin to seem trivial in comparison to the shared challenge of understanding and interacting with life on a galactic scale. Projects to explore, communicate, and protect life may demand unprecedented cooperation, pooling the best minds, technologies, and resources across humanity. The universe becomes the stage on which human unity is tested, not just a distant backdrop. Finally, the discovery forces us to confront the unknown itself. What does alien life think of the universe? How do we interpret its signals, its existence, its behavior? If intelligence exists there, Even in rudimentary forms, it is living proof of the universe's creativity, its capacity for diversity, and its openness to possibility. The profound realization is that the universe is not a static backdrop for human drama. It is a living, dynamic arena in which life, in countless forms, plays its endless, intricate game. In the quiet moments beneath the night sky, one can feel the weight of this knowledge. Life is not an accident confined to Earth. It is a phenomenon that occurs wherever conditions allow, and with James Webb's telescope, we have crossed a threshold. The universe is no longer a distant stage. It is alive, vibrant, and waiting for us to join the story. How we respond will define not only our destiny, but our meaning in a cosmos that is suddenly, gloriously filled with life. The implications of this discovery extend far beyond science. They touch our hearts, our minds, and our spirits. They challenge our arrogance, expand our curiosity, and invite us to see ourselves as part of something far grander than we ever imagined. The 99.7% certainty of life on a distant planet is not just a number. It is a revelation, a call to action, a reminder that the universe is alive and that our place within it is both precious and temporary. As we close this chapter, we are left with questions rather than answers. How will humanity evolve in response to this knowledge? Will we rise to meet the responsibilities it imposes, or will we falter under the weight of our own short-sightedness? The answers will not come quickly, and perhaps not in our lifetimes. But one thing is certain. The universe has spoken, and life, once confined to Earth, now whispers from across the stars, waiting for us to listen.